Okay, welcome to tutorial 2. This is called Principles Using Intermediate Tools. The goal for this tutorial is to sort of level up the mathematical sophistication from your principles or intro economics class. So what we're going to do in this video is start by reviewing the demand and supply model that you learned in your intro class. We're going to start with demand, build up a mathematical approach. We're going to do the same thing with supply. Then we're going to bring the two concepts together and talk about market equilibrium. Then work through what we call comparative statics. Some of you may have seen comparative statics in your intro class. Some of you will not have. Some of you may have seen comparative statics, just maybe not called comparative statics. We're going to talk about elasticities. And then we're going to close out with taxes. And this is a lot to do in one tutorial, so we're going to move relatively quickly. I'm going to assume most of you have a pretty good conceptual understanding of each of these topics. So the main goal of what we're doing here is just to introduce new mathematical approaches to familiar topics. So let's first review demand. The definition of demand, right, as you all know, is the total quantity of a product that consumers are willing and able to buy at each possible price. So I'm going to do some shorthand on the screen here. If you want sort of a more formalized treatment of any of the definitions, you can take a look at the textbook. So this is really just like a price and quantity relationship for buyers. For buyers at all possible prices. Okay. So what we're going to do next is introduce our mathematical definition. So in this class, we're going to use a lot of sort of more formalized mathematical terminology and notation. So here we're going to say demand is a function, so we'll call this D, and it's going to be a function of some variables. And the demand curve is going to return quantity demanded. So the variables that we particularly care about when we consider demand are three. So first we have price. And this is just the price of the good with the quantity we're talking about. So this is just price. Two, we have the price of related goods. So this could be complements or substitutes. And we'll talk about, there was a great question in class yesterday about the sign, how we think about complements and substitutes when we're talking about the parameters we'll get to in just a second. And we'll walk through these signs on the parameters in just a second. So this is the price of other goods. And third is income. We denote this with Y. Okay. So the way we write this is just that demand is a function of each of these three. So price of related goods, and income. Okay. So let's walk through a relatively simple linear demand function for, let's just use cheese as an example. So we're going to call this linear cheese demand function. Okay, so the way we define our demand curve, so we have D as a function of price, price of other goods, and income. And we're going to set this up as a linear relationship between these three variables. So first we're going to set up our intercept, and we'll just call this alpha. Then we're going to introduce a second coefficient, second parameter, beta, which is what controls the relationship between price and quantity. Then thirdly, we're going to introduce something very similar, but for the price of related goods. So our gamma P0. And this parameter here, gamma, is going to control, the sign of it is going to control whether goods are complements or substitutes. And lastly, we have delta controlling y. Okay. So, as I've already said, these four parameters are what we call, these four terms are what we call parameters. And they're constants, and they're sort of given to us in the problems we're working with. If you ever take an econometrics course, the entire course is essentially about taking data and allowing us to say something about these parameters. That's loosely what econometrics does. Okay. So in this class, the way we define parameters is just that parameters are constants in our functions. In our functions. Okay. So let's actually go through and use some numbers. So for this linear demand function, we're going to set alpha equal to 12, beta equal to 2, gamma equal to 4, and delta equal to 1. Okay, and then on the side here, we're going to write down specific values for our three variables, but we'll substitute these in a little bit later. I'm sorry, for our two variables, we're going to leave price undefined. So P0 is going to equal 4, and income is going to equal 24. Okay. So the first thing we're going to do is plug these parameter values into our demand curve. And we're going to simplify to return a demand relationship between just price and quantity. So first off, we'll plug in the parameter values. So alpha is 12 plus beta, which is 2 times the price, plus gamma, which is 4. And we're going to multiply this by P0 for just a second. Then we have delta, which is 1, so we're going to drop it, and all we have is y. Okay, so this form here tells us the relationships between these three different variables and how they influence the quantity demanded. So I'm going to highlight this And we'll come back to this a little bit later. But the next thing we want to do is to sort of fully define this demand curve. We have more information, and the information we have is about the price of the other goods and our income. So we're going to substitute this in as well. So we have 12 plus 2p plus 4 times the price of the other good, which is 4, plus 24. Okay. And when you simplify all this, okay, again, I think I did this in class. I made a small mistake. We actually have a negative sign in front of our betas. So I'm going to go through and actually erase this to correct it. Okay, negative 2. Negative 2. Negative 2. Okay. And of course, we need beta to be negative because we need a negative relationship between price and quantity for the law of demand. Okay, so simplifying all of this, all of the numbers of our intercept, we get 52 minus 2p. And this is our demand curve. All right. So this gives us a one-to-one relationship between prices and quantities, answering the question, at a given price, how much is demanded? We can apply some calculus here. When we take the derivative of our demand curve, the derivative of quantity demanded with respect to price, and we apply it to the demand curve, we just look at the boxed region, the boxed component of the linear cheese demand function. And that returns for us just beta. So, like we said earlier, all we require is that this be no greater than 0. And sometimes we can write this, sometimes you'll see it defined as being strictly negative. But I like to write this as a weakly negative relationship. Okay, in addition to equations, you've seen in your intro classes, we often describe our models using graphs. By convention, you've likely become familiar with economics graphs that use price on the vertical axis and quantity on the horizontal axis. So something along these lines. This means that if you want to graph a demand function, it's often convenient to solve for price as a function of quantity, where before we had quantity as a function of price. So to do this, we solve for what we call the inverse demand function. Which is just a function returning price as a function of quantity. So let's just, without defining the function itself, let's just write this price as a function of QD. Okay. So let's go ahead and do this for the linear cheese demand equation. So instead of actually going through and solving this on screen, uh, I've already gone ahead and solved it. So I'm going to write it out. This would be a good place to test your algebra skills. I'm confident you all are capable of doing this on your own. So in this case, using the demand equation from before, which I'll underline in red here, we're just going to go through and solve for price as a function of quantity demanded. So this is just negative alpha over beta minus gamma over beta times the price of the other goods minus delta over beta times income, and finally 1 over beta times QD. Okay. So we often care about shifts in demand. So one thing it's convenient to do is define the intercept as its own function, which depends on the price of the other goods and income. So that definition is just everything that's not quantity demanded in this inverse demand function. Okay, so the way we define this is just intercept as a function of price of the other good and income. These are just all the variables that don't affect the slope. So this is just negative alpha over beta minus gamma over beta times P0 and delta over beta y. Okay. And then to sort of fully define this as a function in mx plus b form, we can write this as price is equal to the intercept P0 y plus 1 over b, 1 over beta times quantity demanded. And let's do some graphing because we all love graphs. So you'll remember beta is negative. It's negative 2. So that means we have a downward sloping relationship between price and quantity. And on the vertical axis, the intercept is given to us by the intercept is actually defined as this intercept function taking P0 and y. Then we have a downward sloping relationship between price and quantity, where the derivative of P with respect to quantity demanded is just 1 over beta. And this is, in our case, is less than 0, but for perfectly flat demand curves, which we sometimes see in perfectly competitive markets, we can also make this a weakly less than relationship, a weak inequality. Okay, so let's go through and actually plug in some numbers here just to make the point more strongly. So let's use the numbers from before. So first we're going to go through and define the value of the intercept. And all we have to do is just plug in the parameter values and the variable values that we used earlier. So we have negative alpha, which is 12, over negative 2, minus gamma, which is 4, over negative 2, times P0. But we're given P0, so we'll go ahead and plug this in, which is 4. And lastly, we have delta, which is defined as 1 over negative 2 times 24. So then we can go through and solve this out. So here we have negatives cancel. 12 divided by 2 is 6. Again, negatives cancel. So we have 4 divided by 2, which is 2, times 4, which is going to be 8. And lastly, we have 24 divided by 2, which is 12. So here that just comes out to be 6 plus 8 plus 12, which comes out to be 26. Okay, so that's our intercept term, and we can, if we'd like to, we can write this in on a graph, 26. And for the derivative, we already know the parameter value of beta, so we can just set this as negative 1/2. Okay, so then our whole demand curve equation finally comes out to be price, excuse me, I should say the inverse demand equation comes out to be 26 minus 1/2 QD. Okay. So for the next set of questions, instead of plugging in the variable values that we have used, so P0 equaling 4 and Y equaling 24, we're going to set up this relationship, leaving those variables as variables. So instead of using the fully simplified intercept term, we're going to allow the variables to move. And this is going to give us some leverage over some related questions. Okay. All right, so when we backtrack a little bit, leaving the variable values here undefined, that's going to allow us to solve for sort of a more general inverse demand function. So that just leaves us with 6 plus, so if you're following along on the screen, I'm just taking these values here, and instead of this one, we have 1/2 times y, and for this one, we have P0. So we have 2 P0 plus 1/2 y, and then we have our negative 1/2 times price, excuse me, times quantity demanded. Okay, so this relationship here is going to allow us to answer some questions. So the first question, what happens to the graph if the price of cheese decreases? So on the right hand side here, I'm going to set up just a simple little graph here. Quantity on the horizontal, price on the vertical, and our downward sloping demand curve. Here's our intercept as a function of our variables. So the question here is, what happens if the price of cheese decreases? So this is equivalent to asking for the derivative. Let me write out the question on the screen. What happens when the price of cheese decreases? So, as we've all learned from uh, our intermediate microeconomics class, this is just the law of demand. So when the price of cheese decreases, we know price and quantity demanded are inversely related. So we know the quantity demanded of cheese is going to increase. So we can illustrate this on the graph. We have price 1 and price 2. Oops. So price 1, price 2, and that gives us quantity 1 and quantity 2. So you know price goes down, quantity demanded goes up. Okay. This is a question we can answer with our principles understanding. But what about the second question? What happens when y increases? Okay. So to set this up, we have to think about small changes. So we could do this with small changes, or we could do it with big changes. So to do it with big changes, we just plug in two different values of y. So originally our y was set to 24. So in this case, we could, set a second income level, maybe twice that. So 2 times 24, 48. And we could plug these in and see what happens to price when, when the quantity, what happens to quantity when the income changes. But we're coming into this class with a higher level of mathematical sophistication, particularly calculus, which gives us some leverage over this question. So one way we can approach this is to take a derivative. And the derivative we're interested in is how does the quantity demanded change when income changes? And here, just looking at the equation, right, we have two parts, and they're both on the right-hand side. So this is our inverse demand equation. We can also use our demand equation from earlier, which has quantity demanded on the left-hand side and our set of input variables on the right-hand side. And this is really the equation that allows us to take this derivative. So I'm going to write this on the side here. So QD is equal to 12 plus 4P0 plus y minus 2p. And we'll just run back up and double check. And that looks correct. Okay, so the question here is what happens to quantity demanded when income increases? And this derivative is straightforward, and that's just 1. So this is greater than 0. So this means cheese is a normal good. As income increases, let's box this. And the interpretation here as income increases, quantity demanded also increases. Okay, and this is just the definition of a normal good. Okay. And an inferior good is the opposite, where we say as income decreases, quantity demanded increases. And we can represent this as a derivative. So in this linear demand function, if delta the derivative of the demand curve with respect to y is delta. If delta were less than 0, then this good would be inferior. And if delta were greater than 0, then the good is a normal good. So here we know delta is 1, but just looking at parameters, in a linear relationship like this, we wouldn't even have to take a derivative. We just look at the parameter in front of y. Okay. So here we've already established a way to sort of scale up our ability to answer questions just because we have calculus under our belt. So we're going to take this this approach and apply it to another question. What happens to QD when the price of a substitute decreases? When P0 decreases. So I said this was a substitute, but we're going to leave our interpretation of the other good until the end. Okay. So again, the way we approach this is we just take a first derivative. The derivative of QD with respect, so in this case, the variable we're considering is P0. So in this case, that comes out to be 4, which is our parameter value. Our parameter value of interest is this gamma. So gamma, in this case, is controlling whether the good is a substitute or a complement. So in this case, our gamma is 4. So we know the price of P0 going down is positively related to the quantity demanded. So the quantity demanded also goes down. And as you've worked with in your intro classes, we can sort of plug in and sort of insert between these two variables the law of demand, what the law of demand tells us about Q0. So we have P0 going down. From the law of demand, we have Q0 going up. So the quantity demanded of the other good. And from gamma, we know QD is going down. So in this way, we have this relationship between Q0 and QD, and they're moving in opposite directions. So what this means is that Q0 and QD are substitutes. Okay. So to answer the fantastic question from class yesterday, when gamma is greater than 0, then this is O and well, let's write this a different way. We'll just say then they're substitutes. And when gamma is less than 0, then they're complements. Okay. Another thing we can do at this point is take the derivative with respect, take the derivative of price with respect to the price of the other good. So the original question for the relationship between quantity demanded and prices was really just that. What happens to QD when price of the substitute increases or decreases? But we can also ask a separate question, which is, what happens to price when P0 decreases? And for this one, it's easier, instead of looking at the demand equation, it's easier to look at the inverse demand equation, which is this one here. So the answer to this question is the derivative of P with respect to P0. So to do this, we just look at our inverse demand equation, and we can highlight this 2 as our as the value of the derivative. So this is 2. And if we wanted to look at parameters, we could go all the way back up and identify this value here, which is gamma over beta. So negative gamma over beta. Okay. And in this case, because beta is negative, this is going to be positive. Okay, so another way of framing this question is when price of the other good increases. So instead of using double negatives, we'll use positive. So when one increases, the other also increases. Okay. So just as a general note here, in general, price is the only variable that moves us along the demand curve. So price moves us along the demand curve. All other variables that affect demand shift, rotate, or when we're dealing with nonlinear relationships, can deform the demand curve. And that's all controlled by this intercept term. So just as a summary here, changes in the good's own price cause a movement along the demand curve, and changes in the other variables change with a linear demand curve, change the intercept. All right, next we're going to discuss the other side of the market, supply. So in a similar way to demand, we can find supply using the mathematical notation S as a function of some variables. And this is going to give us quantity supplied. So our definition here is, the definition for supply is the total quantity sellers are willing and able to sell at all prices. Okay. So QS is what the supply function tells us as a function of price and the price of inputs. Okay, so P and PI. So similar to demand, let's just walk through a simple linear supply function for cheese. Okay, so we have QS is equal to our supply curve, our supply function, PI, and this is all equal to phi plus rho times price plus phi PI. Okay. So the expectation here is that the sign for rho is going to be positive, and the sign for phi is, we would expect this to be negative. As the price of inputs goes up, our costs are going up, which is essentially what the supply curve is capturing. Okay, so let's set up some parameter values and walk through something similar to what we did with the demand curve. So we have phi equal to 6, rho equal to 2, phi equal to 8, and then for a variable value, we'll use the price of inputs being 2. So we can just plug these in to solve for our supply curve. So QS is equal to 6 plus 2 times price plus 8 times PI. And then if we wanted to substitute in our variable value, we could do that as well. That would just make this into 16. And once we do that, we can then, I'll do this all in blue, we can then find that this is, okay, again, I should have set phi equal to -8. This is actually -8, which means this is negative, and we have -16. So this gives us 2p minus 10. Okay. So this is our supply curve, and you can see the relationship between price and quantity is positive, which satisfies the law of demand. Excuse me, the law of supply. All right, so again, we're going to use the notion of the inverse function to get the inverse supply curve. So we just invert the relationship to give us price as a function of QS and PI. And I won't solve this all out on the screen here, but it's a good test of whether you can invert functions, whether you can do this. So we have 1 over rho times QS, phi over rho times pi minus phi over rho. Okay. So then, similar to what we did for demand, we can define the intercept term here, which is a function of just one variable in this case. Okay, so on the side here, we'll set up our supply curve. So we have price on the vertical, quantity on the horizontal, and a positive relationship between price and quantity, which is our supply curve. So in this case, our intercept is actually negative down here. When pi is equal to 2. This comes out to be -10. And just for the sake of clarity here, we'll explicitly write out the intercept term here, pi, which is equal to negative phi over rho, pi minus phi over rho. And when we plug in all the parameter values, this comes out to be negative 8 over 2 times pi minus 6 over 2. And so this is 4 pi minus 3. How did we get 10? Okay, so I made a little mathematical boo-boo on the screen. I'm going to redraw our graph. Our math so far has been just fine, but the way we set this up was a little misleading. So we have price on vertical, quantity on the horizontal, and we have a positive relationship between price and quantity. But the intercept term, when we plug in 2 in for our pi, that gives us 8 minus 3, which comes out to be 5. And that gives us a positive relationship here, and an intercept term of 5. And just to verify for yourself that this is in fact correct, we can use the relationship here from the demand curve that we've already solved out, QS, and solve for the inverse, for the demand curve, which is price is equal to 1/2 QS plus 5. So this is our intercept. Okay. So as you remember from your intro class, when the price changes, so we go from P1 to P2, the quantity demanded also changes. Excuse me, the quantity supplied also changes. Q1 to Q2. So here we have movements along the supply curve. But what if we had changes in our underlying parameter values or variable values? So what happens when the price of inputs increases? So just from what we can see here from our intercept definition, when the price of inputs goes up, our intercept term also goes up. So here, because the parameter values, the sign of phi is negative, this coefficient on pi is positive. So just taking the derivative of the intercept with respect to pi, that comes out to be negative phi over rho, which, given our parameter values, is positive. In fact, it's exactly equal to 4. Okay. So we know when pi goes up, then our intercept is going to go up. All right. And so this type of approach really gives us sort of more control over the types of relationships that we think about in microeconomics. We can look at what happens to the supply curve when the price of inputs changes. With the demand curve, we looked at what happens to quantity supplied when price changes, when the price of other goods changes, and when income changes. So what we're going to do next is introduce market equilibrium and bring these concepts together. All right, before we get into equilibrium, let's do a bit of calculus review. And all we're going to do here is just talk about single variable functions and multivariate partial derivatives. Okay, so before solving for equilibrium, you'll see that in the background we have both supply and demand curves, and we have many variables. Both supply and demand are functions of price and other variables. So with a single variable function, let's say we set up y is equal to f of x. And let's make this a little y. When we take a derivative, we write it as dy dx, which is just the same thing as df dx. So we're just looking at the one variable and how it affects uh, the function when it changes. Or another way of thinking about it is the slope on the graph. But when we have multivariate functions like we do here, so let's write out y is equal to two variables, so f(x) and z, and we want to take a derivative, so we care about changes in y with respect to x. We use slightly different notation. Sometimes I switch the notation, so sometimes we're a little bit sloppy with this, but we use this sort of more script D to denote the fact that we're taking a partial derivative. So what we're saying here is what happens to y when x changes, and we're treating z as a constant in the function. So the way we write this is the partial derivative of f of x z with respect to x. And this y here is just being held constant. So that's the notation. Sometimes I'm a little bit sloppy with this. A lot of the times our functions are highly multivariate. If you want a more formalized treatment, take a look at really any calculus textbook, probably the one you've used to study before, has a more formal treatment here. Okay, so we're going to jump into our market equilibrium. Okay, so we've put supply and demand functions together, and we're going to form our model of a competitive market for cheese. You'll recall from your intro class that the main purpose of supply and demand, our supply and demand model taken together, is to sort of make predictions about how price and quantity change in response to various kinds of shocks or policies. So what this means is that price and quantity are what we call endogenous variables. So let's define that real quick. Endogenous variables are variables determined within the model. Oh boy. And the variables that are determined outside the model are what we call exogenous variables. So, for example, an endogenous variable in this model is P, since it's determined by the intersection of supply and demand. QD, QS are all endogenous variables. Exogenous variables are variables that are determined outside the model. So with our example, the linear cheese model, P0, Pi, and Y are all determined outside the model. So here we have price, QD, and QS. And here we have Pi, P0, and Y are all exogenous. Okay. Okay, so when we talk about shocks in our supply and demand system, we mean changes in the exogenous variables. The model then uses these changes in the exogenous variables to tell us how these shocks affect our equilibrium values. So when we shock, we're looking at changes in our exogenous variables and how they affect the variables that are endogenous to the model. So the supply and demand model predicts prices in quantities in equilibrium. And equilibrium is essentially where the system has come to a resting state, and there's no tendency for anything to change except for an external shock. So when we think about shocks, we look at our equilibrium when nothing has changed. We shock one of the exogenous variables, and then we look at what happens to the new equilibrium. This is essentially how our analysis of markets plays out. So let's do another definition here, and then we'll get into some math. So we say a market is in equilibrium when two conditions. One, given QS and QD, no one wants to or is able to change their prices. And two, given prevailing prices, sellers don't want to change Q, and buyers will not change their Q. Okay. So using this definition, essentially we're calling market in equilibrium when buyers and sellers have no incentive to change their quantities or their prices, given the prevailing prices and quantities in the market. Okay, so let's set this up in a way that looks familiar, and then we'll get into our mathematical treatment of familiar concepts. So we have our price on the vertical, quantity on the horizontal, downward sloping demand curve, upward sloping supply curve, and we have our intersection. So this is our equilibrium price, P star, equilibrium quantity, Q star. So you'll remember equilibrium just happens when the curves cross, and we'll sort of walk through sort of the intuition behind why this is true. So let's say the price is below P star. So we'll use red, say price is below P star. At this point, quantity supplied is less than quantity demanded. And so at this point, there's excess demand. Some buyers who want it are not able to get it. So buyers will start to offer to buy for higher prices, and sellers, of course, will not say no. So the price is going to go up. Okay. So when price goes up, quantity supplied also goes up, and we get this movement back towards Q star. And this happens until we reach equilibrium. So we get this sort of dynamic process that pushes us towards equilibrium. when we are outside of equilibrium. And a similar thing happens when price is above P star. We get, quantity supplied is greater than quantity demanded, so there's excess, which means buyers are able to pay less than they currently are, and sellers, because they have excess, they're trying to sell their goods. So they're going to accept a price that's lower than the market price, and so we get this pressure back towards equilibrium, both for price and for quantity. Okay. So let's walk through some algebra. We use the graph to model supply and demand, sort of giving us the intuition for why equilibrium is here. So let's use this plus the example of the linear supply and demand functions that we have already solved for to solve algebraically for the price and quantity we would expect in the market. So we know equilibrium price must be the price that equalizes QD and QS. So let's just set this up. So QD is equal to QS, and this just is coming from this relationship here. In equilibrium, these two are going to be equal. So we'll just go through and write these equations out. If you have these on a separate piece of paper, you can look back at them. I have them here in my notes. So we have alpha plus beta P plus gamma P0 plus delta Y. And this is going to be equal to phi plus rho times P plus phi Pi. So then we can walk through and isolate price. We've eliminated QD and QS from our supply and demand relationships. So the only endogenous variable we have left is price. So going through and solving for this, I'm going to skip a lot of the work here. I'm going to leave this to you to work through. P is equal to alpha minus phi plus gamma P0 plus delta Y plus phi Pi. And this is actually a negative. And that's all over rho minus beta. Okay. So this is our solution for, I'll put a little star here just to denote that that's the equilibrium. This is our endogenous solution this is the solution for our endogenous variable P star. And the reason we can call this in the solution for the endogenous variables that we have no endogenous variables left. You can scour both sides of this and you'll see there's only one endogenous variable, and that's P, and it's isolated. Okay, so we can go through and plug in our parameter values in just a second. But so we'll do that in just a second here. But the next thing we can do is plug P star back into one of the equations for our quantity. So we take our P star variable, our solution to the endogenous variable P, and plug it into either the supply curve or the demand curve. And that's going to return for us the quantity supplied or quantity demanded. which are equal. So we call this, let's keep our coloring consistent. So Q star is equal to QS, which is the simplest of the two equations. So then we have phi plus rho times P star plus phi pi. And this turns out to be pretty messy, so I'm going to go through and simplify this. So we have Q star is equal to phi times rho minus beta plus rho alpha minus, oh boy, we need some more space. I'm going to backtrack a little bit. Q star is equal to, we're going to multiply, we're going to make sure the denominator is the same for each of our terms. And that's rho minus beta. Then inside, we have alpha minus phi plus gamma p0 plus delta y minus phi pi. Then we have to account for all of this, just to be careful here, is multiplied by rho coming from this. Then we need to account for both of these two components. So we have phi times rho minus beta plus phi times rho minus beta. Okay, so this is a wild mess. And we can go through and simplify this. I don't think for the sake of this video it's worthwhile to do. If you would like to, feel free to go through and simplify this. There will be some cancellations, and you'll be able to see that as you work through it. But we're going to skip this for now. The simpler way, because we know some of the parameter values, the simpler way to work through this problem is, before substituting price into our supply curve, we can actually solve for price using our parameter values. So P star, when we plug in our parameter values, we get 6 plus 4 P0 plus y plus 8 pi, and that's all over 4. So when we, it's still pretty messy, but it saves us a bunch of work. Q star, when we plug this in, gives us 6, which is coming from phi, plus, and then we have 2 times price, which in this case is this whole relationship on the left. So we're going to multiply top and bottom by 2. So we have 6 plus 4p0 plus y plus 8 pi all over 2. Or I should say divide top and bottom by 2, which eliminates the 2 coming from the row and reduces the denominator to 2. And then we have negative 8 pi. Okay. And then here we can just simplify this a little bit further to give us 9 plus 2p0 plus 1/2 y minus 4 pi. In your own notes, make sure you can work from one step to the other. This is just a matter of simplifying our relationships here. Okay, so once we have this, we can then plug in some actual values for our 3 variables. So we're going to use p0 equal 4, y equal 24, and pi equal 2. Okay, so we have price here and quantity here. And we're going to go through and solve for the actual values of these two numbers. So p star is equal to 6 plus 4 times p0, which is 4, plus 24, which is y, plus 8 times 2, and that's all over 4. And we can go through and simplify this. So we have 6 plus 16 plus 24 is 40, plus 16 again. That's all over 4. This comes out to be, let's see, 22 plus 40 is 62 over 4, which should come out to be 30 over 2, or 15.5. And for quantity, we have q star is equal to 9 plus 2 times 4 plus 1/2 times 24 minus 4 times 2. And we're just going to simplify this. 9 plus 8 plus 12 minus 8. So these 8s cancel, and that gives us 21. Okay, so these are our actual values for price and quantity after lots of algebra. Okay, so I've probably convinced you of at least one thing, and that's doing all this algebra is a lot of work. Oftentimes we'll use computers to simplify. You won't see many economists sitting around in their free time working through algebra like this. But hopefully this has convinced you at least that the math behind even the simple models, just even a linear model like this, is there's a lot of moving parts. Okay. So next what we're going to do is work through what we call comparative statics. Statics. Okay, so we've worked through our equilibrium. We've solved for endogenous variables as functions of exogenous variables. With comparative statics, we're now going to use the model really for what it's good for. And that's telling us how the equilibrium changes in responses to shocks of exogenous variables. So when we change an exogenous variable in demand or supply, one of the curves shifts. The question though is which curve and how. And this is really what comparative statics lets us do. So let's define this. Comparative statics is using a model to learn how endogenous variables change in response to shocks in exogenous variables. Okay. So first we're going to set up the general problem, and then we're going to work through some specifics. And we've already done a little bit of this, but let's be a little bit more formal. So here's the general problem. Suppose we have some function of p. So a demand function of p. We have qd is equal to demand, which is a function of p, and some exogenous variable b. In the textbook, you can look at a case when we have two exogenous variables, or one exogenous variable in both the supply and the demand curve. Here we're going to keep things a little bit simpler. We're just going to look at the case where we have an exogenous variable that only affects the demand curve. Okay, so we have this equilibrium system here, or we have a supply and demand system here, and we want to know what happens to price in equilibrium when B changes. And that's essentially the problem we confront with comparative statics. So the first thing we're going to do, we found that our equilibrium price is a function of the exogenous variables. So let me write this a different way. Price is the result of some function p star, which is a function of b. And we're going to use this to substitute into our supply and demand curves, our equilibrium solution. So all we're doing here is just saying there is an equilibrium, and the equilibrium price is p star. So in equilibrium, what happens when p changes? Okay, so QD let me write this a different way. D, and we're going to substitute in p star, which is the result of p star taking b, and b, and we have our supply curve, which is also taking p star, which is a function of b. So to answer our question, how does an increase in demand, how does an increase in the demand shifter B affect the equilibrium price? We have this equilibrium relationship between P and B that has to hold in equilibrium. So to do this, we have to differentiate both sides of our equilibrium condition, where we set quantity supplied equal to quantity demanded. QD and QS, and these two are equal. We have to differentiate both sides of this relationship with respect to b. So you're probably used to taking derivatives with respect to x when x is on the right hand side only, but really in mathematics there's no reason we can't take the derivative of an equation where x is on both sides. So in this case we're going to take a derivative with respect to b where b is on both sides. So let's carefully work through this. And in the end, what we're trying to solve for is, we'll just leave this in the top hand corner here. We're trying to solve for the derivative of p star with respect to b. So this is the thing we're looking for. Maybe put this in red just so it's more prominent. Okay, so first we're going to differentiate the left-hand side. So here we have a partial derivative of d with respect to p star. But we also know that p star depends on b. So maybe to back things up a little bit here, just to be more clear, we're going to differentiate qd with respect to b. And that's going to equal the derivative of qs with respect to b. So to simplify, to write this out more formally, the derivative on the left-hand side is the derivative of d with respect to p star. But because p star is also a function of b, we have to multiply by the derivative of p star with respect to b. And because the derivative of, because both inputs into the demand relationship depend on b, we also have to take the derivative of d with respect to the second input b. So here we have the derivative of d with respect to b directly. So we've first taken the derivative of the first input, and then second we've taken the derivative of the second input. And from our derivative rules, we just add these together. So then secondly, we take the derivative of qs with respect to b on the right-hand side. So this is ds dp star. And similar to what we did for demand, we just have to multiply this by the derivative of p star with respect to b. Okay, so let's just identify the part of this relationship that we're going for, and that's this and this. So all we have to do is simplify solving for this value. So to do that, we'll just bring both to the left-hand side. So we have dp star minus ds dp star times dp star db, which is equal to negative dd db. And then, so we can flip the signs, make this positive, make this negative. So then dp star is equal, dp star db is equal to, on top, we have dd db, and on bottom we have ds dp star minus dd dp star. Okay. So this is our answer here. This is how price changes in response to a change in B. So great. So we have this this derivative, but what is it really telling us? So this is similar to asking the question, what sign is this derivative? Is price going up or going down when we change b? Or more specifically, is price going up or going down when b increases? So we know a little bit about the signs of these derivatives. So we're going to put aside the question of what happens on top for just a second, but we know some things about what happens on the bottom. So from the law of supply, we know this is positive. When price goes up, quantity supplied goes up. And from the law of demand, we know that when price goes up, quantity demanded goes down. But this negative value is multiplied by a negative. So the whole bottom piece is positive. So the sign of the derivative of d with respect to b determines whether b shifts price up or price down. So let's say b is income. So when b is an input into the demand curve directly, we know the derivative, if b is income, the derivative of the demand curve with respect to b is going to be positive. Well, if it's a normal good, it's going to be positive, and if it's an inferior good, the derivative is going to be negative. So the relationship is, it depends on whether the good is positive. The good is a normal or inferior good. So really, this may sound like a ambiguous solution here, but the conclusion really is that the formula tells us what determines the relationship between P and B. And it tells us what we need to know about the curves to make a prediction. So really this has told us that all we need to know is the relationship between the demand curve and B. And that tells us what we need to know about the relationship between price and B. So this is actually a really compelling result here. Okay, so this is all about the relationship between P star and B, but we can also think about the relationship between Q star and B. Okay, so it's similar to what we did before. We have Q star, which is just coming straight from either the demand curve. So we had P star as a function of B and B. And we had the supply curve, which is a function of price, which is a function of B. So here we're just gonna isolate these two. We could look at D, but it's simpler to go directly through supply. And so the thing we're doing here, similar to what we did above, is to try to find Q star, the derivative of Q star with respect to B. And to do this, again, we're going to use the chain rule. So we have ds dp times dp deb. Okay. So we don't have to do a lot of simplification here. We know the sign of this relationship is positive from the law of demand, and we know the sign here depends on the sign here depends on the sign of dd dB. So when price increases with B, then the quantity in equilibrium also increases with B, and the reverse is also true. Economists typically summarize the shape of a supply or demand curve using what we call elasticity rather than slope. Elasticity sort of allows us to describe the shape of a curve independent of the units. So whether we choose to have price in terms of pennies or dollars, it doesn't change the elasticity number. Or if you use slope, it does depend on the currency you use. In your intro class, you probably used the midpoint method for calculating elasticities. But since calculus is really about changes that are really small, here, because we have these tools, we can really simplify our elasticity concept. So we're going to work through some examples here and some definitions first. So just set up the definition here. So definition, I'm going to use a little vagary here. We're going to say in general. We'll talk maybe a little bit later about why we have to only state this as a general definition. The elasticity of x with respect to y is the percentage change in x for a small change in small increase in y. And just for completeness here, we'll rewrite this as x, little x. Okay, so then we can define this as epsilon, which you may have seen before. Then we have our sort of classic definition from intro, which is x1 minus x0 over x0. So this is not the midpoint method. We'll talk in just a second, or you'll see in just a second why we don't need the midpoint method. So we have y1 minus y0 over y0. Okay, so we have the change over some starting point. So we can just rewrite this as delta x over x0 and delta y over y0. And because we have our notions of calculus in this class, we can actually, you can see this is equivalent to a derivative. So we're looking at the change in x as y changes, and then we just look at the ratio. So this is equivalent to, so you can do some rearranging if you'd like to show that this is true here, but we have dx, dy, and then we have y over x. So some sort of concept of a change and then some ratio of x and y. Okay. So then we have our general definition of elasticities, and this gives us the ability to apply our elasticities to different contexts. So the first one is going to be price elasticity of demand. So price elasticity and we're going to deviate slightly from the notation in the textbook. I think the textbook's notation is perfectly fine. I generally prefer my notation to convey some information about what is being described. So here we're going to use epsilon subscript d to denote the price elasticity of demand. Epsilon is always going to be elasticity. So here we just have the derivative of QD with respect to price times price over QD. So price elasticity of demand is typically negative. More negative numbers means a greater negative responsiveness, which therefore means the demand curve is more elastic. So, except for a special case of constant elasticity of demand curves, typically the elasticity of demand changes along the demand curve. And we can sort of use a general rule of thumb that elastic demand curves are flatter at any given Q than inelastic demand curves. So you can sort of see this like, so if we have a demand curve that's flatter than another, so D1, D2, so D2 is flatter than D1. This basically means when we change prices, so we go from one price to the other, the flatter one is going to be more responsive. So so we go from Q to Q, what do I call this? Q1, Q1 prime. So this change is much smaller than Q1, Q2 to Q2 prime. So this change is much smaller than this change. So the responsiveness of the flatter demand curve is greater. And we can classify our elasticities as you've seen before. So the elasticity of demand that's less than -1 is inelastic. And elasticity of demand equal to 1 is unit elastic. And an elasticity of demand that's between, you can say between -1 and 0. And let's actually, well, is inelastic. Excuse me, let's fix this here. This is elastic. So it's very responsive when it has a larger absolute value. Okay. So let's actually go through and calculate this for our linear demand curve. So if you'll remember, we had QD equal to 52 minus 2p. And so our elasticity of demand, we're just going to take the derivative of QD with respect to p. So that comes out to be -2. And then we're going to multiply this by where we are. So we have price, which is we can just rearrange this whole equation here to give us price. So that's 2p is equal to 52 minus qd. P is equal to 26 minus 1/2 qd. So we plug that in. We have 26 minus 1/2 qd. And on bottom, we just have qd. All right. So here, we just have to simplify. So I'm going to put the negative 2 outside. On the inside, we have 26 minus, well, actually, before we do this, let's rearrange. So we have 1/2 qd over qd minus 26 over qd times 1/2. And this just gives us 1/2. Oops, I forgot to multiply by 2. So this is going to be multiplied by 2. And this is going to be multiplied by 2. Not by 1/2. Okay, so 2 times 1/2 minus 52 over qd. And this all comes out to be 1 minus 52 qd. And this is our elasticity of demand for our linear cheese demand curve. And you can see we have qd in the bottom here. And what this relationship is telling us is no matter what qd we care about, we can just plug in our qd, and it tells us the elasticity, the instantaneous elasticity of demand at that particular point on the demand curve. And this is cool, right? In the past, we've really only used sort of discrete points on the demand curve. It had to go through and calculate elasticities at any given point. Where here, our elasticity captures any possible point on the demand curve. So we can learn some things about our demand curve just looking at the elasticity of demand. This is just like a personal note here. This is so much better than the intro definition of elasticity and the way we worked with elasticities in that class. So this tells us that as qd gets larger, this whole component here gets smaller. But because it's a negative, we can say as qd gets larger, elasticity of demand, because this part is getting smaller, but the small it's negative, so it's becoming less negative. The elasticity of demand also gets larger. Okay, so we know elasticity of demand and QD are positively related. Okay. Now, so next we're going to look at price elasticity of supply. So we're going to walk through a similar set of steps here. Price elasticity of supply. So the definition is just an extension of our generalized elasticity definition. We're just applying it to the price quantity relationship for sellers. So here it's just the derivative of the quantity supplied with respect to price times price over quantity supplied. So using, well, first let's classify different values here. So elasticity of supply that's greater than 1 is elastic. When we're between 0 and 1, we say this is inelastic. And when it's equal to 1, this is unit elastic. Okay, so let's use the supply curve from earlier. And just as a reminder, put it up here. So QS is equal to 2P minus 10. Okay. So the derivative of QS with respect to P is just 2. So we have 2 times, and then we have price divided by QS. So here we can just rearrange this. We have 1/2 QS plus 10 is equal to P. So 1/2 QS plus 10. I'm sorry, this is a 5. And then we divide it by QS. Okay. So first, we'll break this into 2 parts. We have 2 times 1/2 times QS over QS, which is just 1, plus 2 times 5 over QS. So that's going to equal 1 plus 10 over QS. All right. And this is our elasticity of supply. And so again, we can try to sort of classify the relationship here. So you can see as quantity supplied gets larger, this whole piece, this whole second component is going to 0. And it's going to 0 from so we have 1 here. We have sort of an asymptote at 1. Okay. So we're approaching unit elastic from above. Okay. And you could try to find where, so at some point, when we get closer and closer to 0, we're going out to infinity. So you can try to find the point where we cross different values if you'd like. Okay. All right, so next we're going to look at cross price and income elasticity of demand, and we're not going to actually work through any examples here, but you could, if you'd like to, apply these definitions to the examples we've worked with in the past, because we actually have functional forms which are conducive to working with these definitions. So the first is cross price elasticity. Okay. So just the definition here is um, I'm going to use x. You could use 0, depending what you'd like. Typically, we've used epsilon x as cross-price elasticity, and that's the notation we'll use in this class. But whatever suits your fancy. So we just want to look at the change in the quantity demanded when we change the price of alternative goods. And then we just multiply this by P0 over QD. Okay. And then we say when cross-price elasticity is positive, then P0 is a substitute. And when cross-price elasticity is negative, then P0 is a complement. All right. So finally, income elasticity of demand. So here we just have E epsilon subscript I dQd with respect to y times y over QD. And when epsilon I is positive, then the goods are normal goods. And when epsilon I is negative, then we have inferior goods. Okay. So next we're going to look at government policies. So we're going to look at the comparative statics on an equilibrium with a per unit tax. And we're going to look at comparative statics and elasticities and evaluate the policy implications of a tax. All right, so our last topic for this tutorial is government policy. So we're going to bring together sort of most of the topics we've reviewed in this tutorial. All we're doing next is introducing taxes. So you've seen this before in your intro class. So the tax we're going to focus on is what's called a specific tax, or a per unit tax. So let's just go ahead and define this. A specific tax is a dollar amount of tax per unit sold. And I just want to point out here, this is not the only type of tax. Another type is what we call an ad valorem tax, which is, we can define this too, an ad valorem tax is sort of a percentage of the price. And this is, you'll see ad valorem taxes kind of all over the place, is a a tax, we can say a tax that varies with price. We're not. There's a pretty good example of what we're going to do, but with an ad valorem tax, and you can find it in the textbook. But here, we're particularly interested in what the tax does to the price that consumers have to pay for whatever we're looking at. So here, we're going to use cigarettes as our example. And we're going to look at the effective price sellers are receiving per unit, as well as the tax amount collected by the government and the change in what buyers are facing. So in the absence of a tax, the equilibrium price and quantity for gasoline. Well, I guess here we're talking about cigarettes. The quantity for cigarettes are where supply and demand intersect. So let's first start off graphically, and then we can introduce our math afterwards. And just a side note here, I've been doing economics all of my adult life, and I still prefer to start with a graph and then develop the intuition and translate that into the mathematics afterwards. So if that's your preference, I fully support that. It's no diminishment of your economics intuition. Okay, so in the absence of tax, right, we have an equilibrium, which is the intersection of the price and the quantity. So when we introduce a tax, we're going to call this tau, which is the specific tax in this market on cigarettes. One of the questions we're asking is, how does this tax affect supply? So as you remember, the tax itself doesn't, the results of the tax don't depend on whether we impose the tax on the buyers or the sellers. And the intuition, right, is when we impose a tax, we're essentially just separating the price for the buyers and the price for the sellers. The price paid by the buyers and the price received by the sellers. We're just separating these two. So it doesn't matter whether we're shifting the supply curve up or we're shifting the demand curve down. All we're doing is separating the price for the buyer from the price received by the seller. So we're just creating this tax wedge. Now, so we have these two prices, and we have the relationship between them. We also know that relative to our equilibrium quantity, we have a smaller quantity after the tax. And this is just because we're wedging the buyers and sellers. So as you remember, the incidence of tax is just how much the tax falls. Call this I for the buyers and I for the sellers. And we'll write down the definition for incidence. The incidence of a tax is let's write this specific to the sellers, or excuse me, to the buyers. The incidence of tax on buyers is the share of the tax that falls on the buyers. Oops. Okay. And as you remember, it doesn't matter. Uh, the incidence doesn't depend on whether the tax is imposed on the buyer or the seller. And just for our definitions, I'm not going to write it on the board here, but um, we can just replace this with sellers, and we get the same thing just for the sellers. Okay. And it's just the difference here between what you were paying before the tax and what you're paying now. Okay. So if you'd like a sort of a more formal proof of that that the incidence doesn't depend on who's paying the tax, we can walk through that at a different time. But for now, I'm going to take it as given that you all have seen that before. Okay, so we're going to walk through our equilibrium. And we're going to allow there to be a tax on the sellers. So we've set up the graph, and we're going to think about what happens in response to this tax. So our equilibrium condition, right, is just the demand taking P is equal to the supply taking P. And we have price in equilibrium, which is a function of our tax, tau. Okay. Now, so a little bit of notation here. So when we're going to say this price is the price paid by the buyers. And so we can substitute in our P star as a function of tau into the demand curve. And that's going to return the quantity demanded at the price in equilibrium with the tax. And we know for the supply curve, sellers are receiving P star in equilibrium with the tax, but they're giving up the tax going to the government. So this is kind of the notation. In past, like, often I like to write it as, PB is equal to PS plus tau. Here, just for simplicity, we're going to use this notation. So then we don't have multiple functions going on. But again, notation only matters in that it's a tool for communicating. So if you find this clumsy, if you find any part of what we do clumsy, feel free to simplify the notation, if possible. Okay. So as a note here, before we have a tax, we can just say the tax is equal to 0. So this is our sort of precondition. So we're going to use calculus here to find out how much the buyer's price increases when we increase the tax from 0 to some positive amount. And we'll do it in a way that proves that the burden of tax on buyers will depend on the shape of the supply and the demand curves. So the question here is, so I'll write this out as a question. What is the derivative of P star with respect to tau? So that's our big question. All right. So we have an equilibrium condition, and to answer our question, all we have to do is take some derivatives. So we're going to differentiate both sides with respect to tau. differentiate both sides with respect to tau. So we take the derivative of d with respect to p star. Then by the chain rule, we have the derivative of p star with respect to tau. And that's all equal to the derivative of s with respect to p star. And then we need the derivative of the inside. So that comes out to be the derivative of p star times tau, with respect to tau, minus the derivative of tau with respect to tau. But that's just equal to 1. So we'll just write this as 1 here. Okay, so now we actually have all the information we need here. We just need to rearrange to sort of get us at our main question here. So I'm going to write all of this. Well, first let's underline where our question shows up. And then we will simplify with respect to that derivative. So we'll bring everything onto the right side. So we have d p star minus ds dp star times dp star d tau. And then that's going to be equal to ds dp star. All right. So then we just divide both sides by this blue. So that's going to give us dp star d tau is equal to ds dp star all over, let me be a little more clean here, dp star minus ds dp star. Okay. So this is one way of classifying what we, how responsive, how the price that buyers are paying responds to a tax as we go from 0 to some tax. But there's actually another way of writing this. So what I'm going to do is multiply top and bottom on the right-hand side by p star over q star. So what we get in this case is ds dp star times p star q star. We have dd dp star times p star q star minus ds dp star times p star q star. Okay. So I'm just going to casually scroll up to our definitions of price elasticity of supply and price elasticity of demand and box these. And you'll see that that's what's in our equation here. So using our elasticities and substituting them into our derivative formula, we have d p star d tau is equal to elasticity of supply over elasticity of demand minus elasticity of supply. I think I did something wrong here. I'm just going to double check all the signs are correct. I forgot a negative here. Probably all the astute students in the crowd have been yelling at me for a couple seconds here. So we'll just flip the signs on bottom. Otherwise, multiply top and bottom by -1, and we get elasticity of supply over elasticity of supply minus elasticity of demand. Okay, so let's go through and look at the signs of these values. So elasticity of supply is always positive, and elasticity of demand is always negative. So we know this whole thing is positive, which means this is all greater than 0. Okay, so that's cool. And what the interpretation here is that tax increases P star. Exclamation point. Okay. And we know something about the relationship between the incidence of tax, or the responsiveness of the buyer's price to an increase in tax. We know there's the relationship between dp tau to elasticities. So let's just walk through a little bit of math here. So before we do that, though, let me just make a little note. So we could, so we have, we know, let me write this a different way. P star as a function of tau is equal to, well, the price the buyers are paying is this, and the price the sellers are receiving is this minus tau. So the incidence of tax is going to be this derivative for buyers, and is going to be 1 minus this derivative for sellers. So the yeah, so we can write the whole thing out sort of in terms of the incidence on sellers as well. So yeah, there's a little bit of a note about this in the textbook. It's not the main thrust of what we're doing here, but I just wanted to sort of highlight this, that this is how the seller's price responds to changes in tax. Okay. So the next thing we're going to do is look at, we're just going to sort of walk through a couple of cases here. So if you think back to possibly one of the exercises you've worked through in intro, let's set up two examples here. So one where we have very steep supply and very flat demand, and the other where we have very flat supply and very steep demand. Let's actually try to get the equilibrium price relatively similar in both of these cases. Okay. Now, if you remember, when we impose the tax wedge, we slide it in from the left. Okay, they're not exactly equal, but hopefully for what we're doing here, this is going to be good enough. I have not drawn this properly. Let me redraw this here. So we want a flat supply curve and a steep demand curve. What am I doing? Okay. All right. Okay. This is much better. Okay, so we have the tax here. And so the idea is the incidence of tax falls much more on the buyers when the demand curve is relatively steep, and falls much more on the sellers when the supply curve is relatively steep. And so the idea with our derivative solution to the incidence of tax on the buyers that we just walked through is we should be able to pick up this idea in the graphs here in our responsiveness to tax, because we're picking up elasticities as the answer to our solution. So let's walk through a couple examples here. So what if we have an elasticity of demand of 0? So it's the responsiveness of the demand curve is very low, which corresponds more to case 2. So in this case, our d p star d tau is we'll just say it's close to 1 when elasticity of demand is close to 0. I'm going to write this a little bit bigger. Elasticity of demand is close to 0, then most of the tax falls on the buyers. Now, when we're in case 1, and elasticity of supply is close to 0, and sellers are relatively less elastic, then you can see the derivative of p star with respect to tau is very close to 0, because the top part here is roughly 0, and this part here is roughly 0. Okay, so this I think is pretty cool. Where we've defined the responsiveness of the price in equilibrium with a tax uh, purely based on elasticities, which makes sense with our intuition. Okay, so in the next video, we'll be animating uh, constrained optimization. So we're going to move beyond what we've seen in intro, and we'll talk about how buyers use their budget constraint and their utility function to solve their uh, optimal choice bundle.